AI agents have integrated into web development workflows. They write code, launch browsers, inspect the results, and manage the entire iteration loop. This works because web applications are transparent. Through Chrome DevTools, an agent can programmatically read the HTML DOM, check element states, and execute clicks. But turn that exact same agent toward a legacy desktop environment, like WPF or Java Swing, and the loop breaks. These fat clients are architectural black boxes. They lack a standardized programmatic access port to expose what their user interface is actually doing. To interact with them, agents rely on external screen scraping. They take literal screenshots and try to decipher the application state pixel by pixel. Mapping mouse coordinates and reading text through OCR is brittle. A single layout shift breaks the automation pipeline, making complex UI testing slow and lossy. Without a direct line to the interface, mission-critical desktop applications remain invisible to the modern autonomous AI development loop. In a server backend, you query a database to find out exactly what state a system is in. In a desktop application, that state lives entirely in memory. It is scattered across thousands of runtime objects, deeply nested visual trees, and dependency properties inside the CLR process. The behavior driving these applications is nonlinear. It relies on a dense web of routed events, triggers, and callbacks reacting to user inputs. Over decades of development, this creates emergent behavior. Small, undocumented workarounds layer on top of each other until the UI operates in completely unpredictable ways. This is why legacy rewrite projects often fail. Developers rebuild from the outside, missing the invisible micro-behaviors that users rely on every day. Existing accessibility tools like Microsoft's UI automation are insufficient for this task. Because they were built for screen readers, they only expose a narrow fraction of the actual visual tree. Understanding a running fat client is strictly an observation problem. You cannot solve it from the outside. You need internal access to the application itself. Instead of trying to pry the application open, we embed the observer directly inside the running process. This is the WPF MCP Inspector. It is a lightweight HTTP server embedded directly into the fat client. By binding this server to localhost port 9222, it mirrors the default port used by the Chrome DevTools protocol, aligning the desktop environment with existing AI workflows. Running in process means the server has full clearance. It can safely walk the UI dispatcher threads and extract raw data bindings without requiring complex IL rewriting or external debuggers. The entire complex visual hierarchy is serialized and instantly translated into clean, structured JSON. This payload maps every interactable ID, reads the active text, and accurately flags visibility and enabled states. Because it reads the runtime tree directly, even entirely custom controls and deep styling templates become fully introspectable. This inversion of observability takes an unreadable, compiled binary and turns it into a self-documenting, queryable API. The embedded MCP server exposes this data through a standard REST interface. Calling the get/tree endpoint maps out the entire structure for the agent, instantly returning every discoverable, interactable element on the screen. For granular details, the agent uses get/component. This deep dives into the exact microstate of a single dropdown, text field, or list item. To interact, the agent sends a post/action request. This translates semantic commands like clicking a button into actual UI events. The moment the action executes, the updated component state is immediately returned in the response payload, giving the agent instant confirmation. If visual verification is required, a screenshot endpoint captures the exact current window state as a digital image representation. Combined, these sequential endpoints replicate the instantaneous feedback loops that JavaScript developers have used for years. They grant AI agents the exact same programmatic control over a legacy desktop app that they possess over modern web applications. To prove this architecture works in production, consider YouTube Fetch, an AI agent, Claude Code, developed, tested, and iterated upon this entire WPF application using the embedded MCP server. The agent queried the UI, navigated preferences dialogues, and validated system tray integrations, all without requiring human help. When an error occurred, the agent read the raw component state, identified the misaligned property, wrote the necessary code fix, and restarted the application to test it again. It could even trigger a complex download action and programmatically verify the system's progress in real time. The agent verified all updated UI states by parsing the exact JSON responses, bypassing the need for image diffing. YouTube Fetch proves that an LLM can architect, launch, interact with, and finalize a native WPF app by itself. Visual elements are just the outer layer. Complex applications hold highly specific backend data that standard UI controls might not expose. By registering an app state provider delegate, developers can open up a get/state endpoint. This exposes deep business logic and underlying data structures directly to the AI agent in a readable format. Exposing this programmatic API creates a massive advantage for automated regression testing. This diagram compares testing methods side by side. On the left, a 1-pixel shift fails a visual test. On the right, comparing the JSON trees highlights the exact property value that actually changed. It also means business analysts can methodically query the live application to accurately document how legacy workflows operate in production today. Structured internal observation eliminates the problem of building blind. You no longer have to guess what the application does before attempting to modernize it. While this specific implementation targets WPF and the .NET ecosystem, the architectural theory is framework agnostic. The exact same embedded HTTP server pattern has been successfully deployed for Java Swing applications by walking the AWT component hierarchy. This pattern scales to C++, Qt, and GTK interfaces using their respective property systems. The value of this tooling scales with the size of the application, especially on 100,000-line codebases with years of technical debt. This inspector is not a code generator. It provides the visual and state data required for an agent to understand a running process. By giving legacy FAT clients the ability to serve their own exact state over HTTP, we upgrade opaque technical debt into transparent, AI-manageable infrastructure.